Mr. Muhammad Aziz serves as journal editor in Applied Energy, Applied Science, Energies, Processes, Sustainability, and Carbon Resources Conversion. The research area of Mr. Muhammad Aziz is in energy systems, process design, power generation, carbon capture and storage, hydrogen production, renewable energy, energy conservation, energy and exergy analysis, exergy recovery, electric vehicle, batteries, and smart grid. The award obtained by Mr. Muhammad Aziz for the last 3 years, the first is Best Paper Award in Energy Engineering category in the 6th International Conference and Exhibition on Sustainable Energy and Advanced Materials in 2019. The second is Top Peer Reviewer Award Engineering and Croffield Pablons 2019. And the third is Yu Tokyo Young Excellent Researcher, the University of Tokyo in 2019. Okay, without further ado, I would like to of Engineering Muhammad Aziz to deliver his presentation. Mr. Muhammad Aziz, the floor is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, Mas Nurul, and also thank you for to all of you actually. I think it is very good afternoon in Japan, and I think also very good morning in Indonesia, and also especially in Saudi Arabia for my guru, Prof. Anton actually. Okay. It is my great pleasure to be invited and also to deliver my talk today, and because I delivered the talk after Prof. Anton, so I think it is very hard time for all of you after getting lectures, important lectures, very valuable lecture from Prof. Anton, and also before that, I think I just would like to talk something that's quite light. Okay, it's not so hard for all of us, I think. So in case that you have any questions, something like that, please raise hands or although it is during my talk, something like that. So I would like to have any kind of more mutual dialogue or mutual discussions with all of you. Okay, I just would like to share my slides for today. Okay. Can you see my slides, Nurul? Everything's fine there?
Yes.
Okay, it's good. So let me stop. Okay. For today, actually, because my background is basically mechanical engineering, and what we are doing now currently is related to the energy systems, and because we are also doing any kind of multidisciplinary research. Now today in our research, in our laboratory in Tokyo University, we are focusing on basically 3 multidisciplines fields: mechanical engineering, chemical engineering, and also electrical engineering. So for today, I think there will be quite multidiscipline also. What I would like to talk today is correlated with the sustainable energy systems toward the green community. So I think this topic is also quite common. I think all of you maybe has interest for this topic also. Okay. As the introductions for my talk today, I think all of us have quite familiar with these 2 buzzwords: Industry 4.0, also Society 5.0. And as we could see over here, that Industry 4.0 comes from Germany. Society 5.0 has been initiated by Japanese ones. Okay, when we check the history also, like different paradigms in the society also finally initiate any kind of different ideas also. Like when we discuss any kind of smart city in about 2010, something like that. In Japanese case, we are not, we didn't like to use the smart city words. So in that time, actually, in that times, because what? Because we really understand that when we are building any kind of city, we are building any kind of energy or any kind of industry, we cannot neglect or avoid any kind of cultural backgrounds, any kind of society developments that we are targeting for whether for the industry or maybe for the society development itself. So that's why the paradigms are, although these two paradigms, they are sharing similar ideas, but actually the backgrounds and also the methods itself are quite different. In Industry 4.0, we are more focusing on the industrial developments itself, but in Society 5.0, we are focusing on the civilizations. And now the buzzword in Society 5.0, we are still focusing on the smart society or any kind of how we can realize the developments of the ultra smart society itself. And why we use smart society or Society 5.0 rather than Industry 4.0, because also we actually realize that we are facing several problems, especially for the cultural, for the legals, for the social problems of the like that. And I think these problems are quite similar for the Asian countries, including I think for Indonesians also, I think. And what we are currently realizing the problem is that the first is correlated with the problems of the legals, agencies, ministries, bureaucracy, or etc. And I think that's also quite similar with the Indonesian case also. And the second thing is with the legal systems, war of technologies, it is correlated with the social acceptance. Not all of the social members, the society, are quite ready to accept any kind of new developments in the technology. That's also correlated with any kind of educations, with correlated any kind of technological mastery. And also the fourth one is also correlated with the human resource, how we can build any kind of quite ready or quite developed capacity for all of the stakeholders. And finally, also the social acceptance. And the big idea in the Society 5.0 is that we are not only focusing on the physical developments, but our target is that how we can actually utilize our creativity, our imaginations, our visions to get any kind of better life, and also to facilitate all of the diversity that we have in society. So the development is that itself is not belonging to any kind of certain society members, but how we can facilitate this kind of developments to be applicable, or also all of the stakeholders can join and can participate, and also finally can taste the result of the developments. And in these ones, so we are dealing with any kind of digital transformations, any kind of green transformations, any kind of corporate transformations, any kind of education transformation, or any transformations. But when we are talking about the transformations tools, we are talking about the physicals, or maybe about the methods we would like to develop, we would like to use. But the main target is that when we have any kind of creativity, when all of the stakeholders, they have their own visions, something like that, how we can facilitate these kind of visions. And finally, we can create any kind of value creations to the society. Okay. Featurings about the Society 5.0. In the Society 5.0, we are talking about several points that's quite, I think, also quite important for us to understand, also to know that. But as I mentioned previously, that the main target for the Society 5.0 is that we are not only talking about the problem solving that we are facing today, like climate change or etc., or any kind of job creations or etc., but also how we can create any kind of value in the society. So the society, all of the society members can have any kind of opportunity, equal opportunity to get this kind of value. And also I mentioned previously that also it also deals any kind of diversity. It's like in the Indonesian case, we have many diversities, including the race, including the religions, languages, backgrounds, or etc., or maybe levels of education level or capacities. And also, when we are talking about the futures developments for the society, we will not only talking about the urbanizations, people move to any kind of big cities, but also I think we need also to develop any kind of decentralizations. Decentralization so far here is that maybe it is quite And it's not the problems of like developing countries, but also for the developed countries like Japan and also the European countries, we are facing with any kind of decreasing populations. Decreasing population usually also followed by any kind of urbanizations, and finally any kind of certain cities or certain area, finally they don't have any kind of opportunity to develop themselves. And also the big issue correlated with this one, also correlated with the resilience. It is not only dealing with any kind of emergency conditions, any kind of disaster or etc., but also the resilience of our years also correlated any kind of non-physical resilience. So in case of Indonesians, I think it is very important also that we realize that we have many diversities, including the religions, races, or etc. How we can utilize this kind of diversity, and finally we can create any kind of social resilience in our society. And okay, I think dealing with any kind of industry 4.0 and society 5.0, okay, everything should be targeted in accordance with the SDG or Sustainable Development Goals issued by the United Nations. But for Indonesian case, I think we have focused on 10 fields, especially for the cities, energy, disaster, also. And when we are, as I mentioned previously, digital transformation on a kind of, when we are dealing with any kind of energy, usually we are also dealing with any kind of green transformations or GX. But basically, like the GX, like any kind of corporate transformations, any kind of social transformation, education transformations, basically also we develop and we base into development in the digital transformations or DX itself. In DX, I think it has been also previously mentioned partly by Professor Anton, actually. So in this case, for the digital transformations, we can utilize any kind of IoT, and also how we, after we are getting any kind of big data from the systems, especially for the energy and especially for the society, like that, how we can process this kind of big data, and finally this kind of big data can be useful for all of us. And we can have any kind of data processing technology, digital twin technology, artificial intelligence, or etc. And finally, when we have translated, when we have produced any kind of values from any kind of big data, and finally how we can communicate with the system itself. As Professor Anton previously mentioned also, he focused on robotics. And how do we communicate it from the big data to the process data, and finally from the process data to the robotics. And finally, it will be very, very useful and or give any kind of impacts, physical impacts to the human itself. And also any kind of another technologies, including the distributed ledger technology, such as the blockchains or etc. I just would like to remind to all of us that digital transformations, on a kind of transformations that we are dealing with now, are the tools. Basically, they are not the targets that we would like to have in the futures. They are the tools that we need to utilize well. So any kind of transformations that we are having now, actually, what we like to do is that how we can create any kind of good cultures, any kind of good characteristics, and finally we can build any kind of capacity. This kind of target is very important for all of us. So the big developments, the big targets for the developments is correlated any kind of capacity developments or capacity building for all of the society, all of the stakeholders inside the society, and finally all of the society members can have any kind of opportunity to have any better life. And okay, focusing on the energy. When we're focusing on the energy, I think about the main pillars in the energy systems. We are dealing with any kind of minimally 3 pillars are very important in the energy systems: energy security, energy equity, and finally the environmental sustainability. For the energy security, we are not only talking about how our systems or how the country can supply the required demand of the energy of the systems, not only like that, but also we are dealing with any kind of how our systems can provide any kind of high quality of the energy. So things, but also we are talking about the qualitative things. Okay, for very simple understandings, like okay, for the quantitative, it means that we are building the power generations. So power generation, the capacity of the power generation should be minimally same with the demand itself, with the amounts of the electricity that we consumes by the society, by the community itself. But when we are talking about the quality, but the quality of the energy, it means that how far our systems can responsibly covers to any kind of fluctuations, any kind of changes in the systems. Okay, in case that we don't have any capacity to provide any kind of system which is responsive to any kind of fluctuations, we will have any kind of imbalances in the systems. So for the examples, like the huge frequency change, we have 50 hertz in our energy, with our electrical grid actually. So the frequency can fluctuate. For in recent case, the fluctuation is really huge, but 0.5 hertz. So 0.5 hertz is really huge for the energy systems, for the electrical grid itself. And also the second thing is that correlated with the fluctuation correlated with voltage. Sometimes voltage drops down to about 160, or maybe it raised to about 150, 250, 280, something like that. Usually in any kind of energy system, usually for 200 or 220 volt systems, the tolerance is about 10%. So I think it is very important to all of us to really understand when we are talking about this energy security, we are not only talking about the quality, but the quantity, but also about the quality. And also the second point is correlated with the energy equity. For the energy equity, we are not only talking about the economy, no, we are talking about the opportunity. Especially, we can imagine like in the futures, we have any kind of large scales of renewable energy. As we know that renewable energy is basically widely distributed, but it is thinly distributed. So it is really quite hard to build any kind of large-scale power generation based on renewable energy. It is literally different with any kind of coal or natural gas-based power generations. So in this case, how far we can facilitate all of the stakeholders, the residentials, the customers, something like that, they have any kind of opportunity to take part or to participate to the grids itself. So in simultaneous manners, we can behave as the producers of the energy and also as the consumers of the energy. So the buzzwords like the prosumers, producer and the consumers in the same times will be quite important in the futures. And also it is correlated also with the demand response in the futures that we need to have. And also finally, correlated with environmental sustainability. Okay, I think all of you quite understand about these ones. So finally, when we can create or we can mutually pillars, we can have any kind of quite good energy resilience in our energy systems. Okay, we are talking like Indonesians, we are targeting for having a kind of zero carbons in 2060, Japan in 2050, Europeans also in 2050, or some countries also in 2050 and 2060. But we must really understand that now, from now on, we are in the transitions mode, in the transitions period, how we can achieve the goals for creating any kind of zero carbons. And this is very huge homework for all of us, a huge task also for all of us. And so that's why we need actually to create and also to establish the roadmap to finally achieve the zero carbons in 2050 or 2060. So for the energy transitions to achieve any kind of zero carbons, we can have any 4 issues or 4 years. But these top 2 issues, I think, correlated with decarbonizations. Decarbonizations means that, okay, we can decarbonize from any kind of carbon-based fuels to any kind of non-carbon-based fuels, or otherwise we can use any kind of renewable energy. Or any kind of, decarbonization is not only limited to utilization of renewable energy only, no, but also it is still okay for us to utilize any kind of carbon-based fuels, any kind of fossil fuel, something like that. But it is very important that how to avoid any kind of CO2 emissions during the utilizations. So it means that when we are dealing with any kind of carbon-based fuels, we need to convert this kind of carbon-based fuels initially to any kind of non-carbon-based fuels, such as hydrogen, ammonia, or etc. And finally, we can utilize that. We can consume this kind of energy, and finally, we don't emit any kind of CO2 during the utilizations. And also the third pillar is correlated with the energy productivity or energy efficiency. And finally, in case that we don't have any kind of options or any kind of technologies to do any kind of decarbonizations also for the energy efficiency. Finally, we must really understand, or we should establish any kind of scenario which can reduce the CO2 emissions itself. And this is the CO2 emissions during pandemic, something like that, but I think all of you also understand about this one. We have reduced CO2 emissions now currently, and now we are enjoying any kind of more fresher air compared with 2 years before, actually. So the problem is that whether we would like to return back to the conditions before COVID-19, or we would like to maintain these conditions, that depends on to all of us. Okay, that's depend to all of us. And we are talking about the energy systems. As I mentioned previously, that this kind of technology also basically based on the digital transformation technology. And over years, we have also adopted any kind of Internet of Energy. So it means that all of the energy systems are basically connected. So the data for power generation by renewables and energy consumptions by any kind of residentials, any kind of offices or etc. are basically accessible. And then we can have any kind of predictions, any kind of more better balancing capacity in our energy systems. And so that's why we can have in the futures, we can have any kind of more real-time pricings, any kind of more balanced electrical grid, and also more balanced energy systems or etc. That's the things that we need also to develop in the futures. Okay, this is about the big data, but I think because limited time, I think I just would like to skip this one. And also about the smart city, about the community energy management, I just would like to remind to all of you that as the trends in the future is correlated with the decentralizations. Decentralizations, not only the cities itself, but also correlated with the energy systems. As the natural characteristics of renewable energy is basically thinly and widely distributed. So it means that we need also to facilitate this kind of decentralizations or any kind of distributed energy systems in our futures energy systems. And for the smart energy systems, you have several options for the smart electricity grid, smart thermal grid, smart gas grid. But I think for Indonesian's case, we are dealing with any kind of smart electricity grid because we don't have, until now, we don't have any kind of thermal grids and also gas grid. Gas grid is, I think, is very limited to certain areas, something like that. Okay, for the smart electricity, we are dealing with any kind of smart technologies, especially how we can actually correlate the information technology with the information data, with the electrical data, and also with the electrical technology operators. So in this case, we are not only dealing with any kind of producers and consumers, which are they are divided, but in the futures, producers and consumers, they are mixed together. They can behave simultaneously. Okay, we can consume the electricity while we're producing the electricity, or etc. So in this case, that there will be any kind of active or mutual correlations and also interactions between the producer and also consumers, or among the consumers or among the producer itself. So the system should have any have any capacity or capability to facilitate this kind of communications, data sharing, or etc. And also the systems must be able to facilitate any kind of self-healing. So in case there is any kind of emergency condition and kind of fault in the systems, so it means that the system should be able to self-heal as quickly as possible. And also there will be any kind of trend for the demand response. So it means that until now, for the conventional energy systems, basically the supply side follows the change in the demand side. But in the futures, no. In the futures, no. Because what? Because supply side, both supply side and also demand sides are changing, are fluctuating. When we are dealing with any kind of renewable energy, means that in the supply side also there will be changes. So how we can facilitate this two kind of fluctuation, this kind of dynamic changes between the supply side, also the demand side. So it means that we need any kind of, the first thing is that correlated with the behavior change. And the second thing is that how we can buffer or facilitate or absorb this kind of fluctuations. That's also very important. And dealing with any kind of behavior change for energy consumption, for energy productions over years, we are also have any kind of demand response technology. So it means that now currently we as the consumers, we need to have any kind of active or dynamics behavior change. So the price of the electricity maybe will change, dynamically change time over time actually. When we see that the electricity, the price of the electricity increases, we can avoid any kind of activities which consumes huge electricity or something like that. So it means that there will be any kind of more active or dynamics interactions between the producers and consumers and also the whole systems itself. And this is the concept of smart electricity, but I don't want to talk further about these things. This is the transformations that we need to have in the futures. Currently, we have three different generators over years. Baseload generators basically covered by any kind of coals, any kind of nuclear or etc. And also we have also any kind of middle load generators or something like that. And finally also we have any kind of renewable energy generators. But because now currently we have limited capacity to adjust or to cover any kind of fluctuations due to the renewable energy, what we really have now currently is that we need finally we need to curtail, or we cannot utilize all of the electricity or the energy produced by the renewable energy. Because what? Because the capacity and also the capability of the grid or the energy systems to balance it. So finally, like in Germany case, actually, what really happens over there, the electricity generated by wind farms in the northern part of the Germany finally cannot be transferred to the southern part of the Germany. Southern part of the Germany basically is, okay, they have huge populations over there. Okay, more denser populations compared with the northern part of Germany. Finally, because of this kind of grid limitations, finally the electricity cannot be transferred, and the wind farms in the northern part of Germany finally are curtailed, or some of them are basically don't operate anymore. And what really happened also because of this kind of fluctuations in Germany also, although the share of renewable energy increases, the total CO2 emissions doesn't change significantly. Because what? Because to cover this kind of fluctuations, finally they also operate any kind of nature. CO2 emissions doesn't decrease significantly. In the futures, what we would like to really have for years, okay, the coals maybe is replaced by any kind of like nuclears or more any kind of greener baseload generators or etc. And also to avoid any kind of curtailments, it means that we need to adopt maximally or optimally all of the renewable energy. The problem is that how we can create any kind of these adjusting generators over years. Adjusting generators, like we can, in case that there is any kind of surplus electricity or any kind of unused or unutilized energy, something like that, we can absorb and convert to any kind of energy which can store effectively, like the hydrogens, like the ammonia or etc. Depends on the times that we would like to use. For the hydrogen, maybe it can be utilized for the short term, and ammonia for the long term of energy storage. And this is when we are talking about the zero carbons, about the carbon-free energy system, something like that. Okay, in our energy systems, we are talking about the primary energy sources. We are talking also about the secondary energy resources, but conveniently, practically in our daily lives, we don't use anymore the primary energy sources directly. We don't burn the coals, we don't burn the wood for cooking or etc. anymore. But now currently people more enjoying to use any kind of electricity, which is really convenient or comfortable to be utilized. So when we are talking about the carbon free, so because the object of the carbon free, it means that during utilizations, during the consumptions of the energy, we don't emit the CO2 itself. So I think in my understandings, minimally we can have 4 types of carbon-free secondary resources. Electricity, yes, this is the secondary resource which has the highest energy efficiency. And finally, also the chemical energy, which is because when we are talking about the chemical energy, basically we only have the option for the carbons and hydrogens. Unfortunately, when we are dealing with the carbon, means that we are emitting the CO2 during the utilizations. So it means that we can have hydrogens over here or hydrogen-based fuels, including the ammonia or any kind of fuels based on the hydrogen itself. Also, we can have any kind of metal fuels, okay, any kind of like aluminums, irons, magnesiums, or etc. When we oxidize this kind of metal fuels, we can generate the heat or etc. And finally, also we can have a heat of use. But when we are talking about the practical applications or utilization in the futures, things in terms of energy security and also energy equity, and also about the technological mastery, technological readiness, or etc. We can have, I think we can have minimally 2 options: electricity and also chemical energy. Chemical energy over here is because we are not dealing the carbon itself, so it means that we are dealing with the hydrogen-based fuels itself or chemical energy over here. So the problem is that electricity and also hydrogen-based fuels from any kind of primary energy resources effectively, and also how we can convert them mutually and also utilize them mutually together. And also the third point, also how we can effectively store this kind of electricity and also hydrogen-based fuels effectively. That's very important for us to all over in the futures. And this is the hydrogen ammonia applications. We can have basically because hydrogen is basically has very high gravimetric energy density. So it means that the applications which need high gravimetric energy density basically is quite preferred for the hydrogens itself, including the aviations, maritimes, train buses. I don't mention about the passenger cars because for the passenger cars, I believe that electric vehicles will be the winner compared with the hydrogen-based vehicles. And also another applications for the hydrogen, which is very huge, is replacing the current running carbon-based power generations to any kind of hydrogen-based power generations. This is the big scales of utilization of hydrogen itself. And this is the prior integrations for hydrogen ammonia in our energy systems. But I don't want to talk technically about these things. But I just would like to share that there are some technologies, and we need to be wise how we can utilize this kind of hydrogens or ammonia in our energy systems. Okay, the price of the hydrogens is still very high. It's about now currently when we use any kind of natural gas, the cost of the price of the hydrogen is about $1 to $1.5 per kilograms. But when we are now for the current conditions, when we utilize any kind of renewable energy, the price of the hydrogen can be doubles or maybe about 5 times of that. So the problem is that, okay, when we utilize this kind of hydrogens only for the quantity services, it means that, okay, we produce the electricity, and electricity only sold for any kind of quantity services. So we think that this kind of this hydrogen price cannot be covered at all. The important thing is that how we can move from any kind of quantity services to any kind of quality services. So we can utilize the hydrogen as the adjusting generators for all of us. So it means that we can convert any kind of excess electricity from the grid when we have any kind of large scales renewable energy, and there is any kind of large access of the energy, we can convert to hydrogen. So it means that the price of the hydrogens will be low, and also we can utilize this kind of hydrogens basically for any kind of quality services. So including, I think, the utilization for the internal combustion engine, fuel cells, and also the combustion with to the existing coal-fired power plants will be really important to all of us. And for the Indonesian case, I think we can adopt this kind of possible roadmap because what? Because we are developing countries and we don't have any kind of sufficient investments and also sufficient technological mastery to adopt the for our domestic utilizations. So I think the big scenario will be, first, we can focus on the export-oriented, and finally, also we can, at the second stage, we can also utilize the hydrogen for any kind of domestic large-scale utilization. So, domestic large-scale utilization over here, I mentioned that I think it can be utilized for any kind of co-combustions to the existing coal-fired plants, to any kind of diesel engines, or etc. So, I think that the fastest technology and also quite ready technology that it can adopt for near futures. I think about 5 or 10 years in the futures. And finally, then we can adopt when we add the infrastructure for the hydrogens, and also some hydrogen economy maybe can be realized at the times. We can have any kind of more wider domestic utilization for all of us. I think it can take about 3 decades or maybe 4 decades in the future. So I don't know about 2060 whether we can really catch the zero carbons. But I think it's quite hard for all of us to catch the zero carbon 2060 because we really need to be wise how we can utilize the currently running coal-fired power plants, and also how we can move from any kind of carbon-based to any kind of non-carbon-based fuels after that. And this is the initial possible scenarios for the Indonesian case, but just would like to skip this one. But as I mentioned previously, we have large scale of resources for the lowering coals, and this is quite unutilized, and also for the industrial agricultural waste and for the hydropowers. I think these kinds of resources are quite potential to be converted to the hydrogens, and hydrogens also can be transported or stored in the compressed hydrogens and the liquid hydrogens, and also the ammonia. I don't want to talk about the methanol, because what methanol, when we are dealing with the methanol, we are still dealing with the carbons. So when we are utilizing methanol, it means that we are still emitting carbon dioxide itself. And also for the utilizations, I suggested that for the combustion to the existing coal-fired plants, and also for the diesels, because we have many diesels for power generation, so it means that we can blend, we can combust hydrogen-based fuels, hydrogens, and also ammonia to the existing coal and also diesel power generations. And finally, in case that the investments and the social acceptance from the community increase, well, we can adopt further technology, including the fuel cells, and also I think dedicated hydrogen-based combustion technology. And I think this is also another technology that we can adopt in the futures, including the utilizations of electric vehicles. And it is quite correlated strongly with the hydrogens, because when we are talking about hydrogens, it will be correlation between the power to hydrogens, or P2H. When we are talking about the vehicles, there will be great correlations between the power and the vehicle, P2V or etc. So I think this is a good deal. This is good actually store the electricity in terms of the chemical energy, which is the battery itself, or also we can convert the electricity, the excess of electricity, to hydrogens, and finally hydrogens can be returned back to the electricity, and actually they can be utilized mutually together. And this is the technology that we have developed, and we have also a big demonstration project in Denmark until 2019, and we develop any kind of aggregator systems, how we can aggregate, how we can operate all of the distributed electric vehicles across the country. As we could see over, like Indonesian's case, we don't have, until now, we don't have any kind of large-scale electricity storage systems, including the pump hydro or etc. So it means that we don't have any kind of sufficient buffer to maintain any kind of high quality of electricity in our electrical grid. So it's quite similar with the Denmark case. In Danish case or Denmark case over years, they don't have any kind of large-scale power storage over there. So finally, they just would like to encourage their citizens to buy the electric vehicles, and then we can operate or aggregate or also can communicate all of these kind of electric vehicles. Basically, all of these electric vehicles can be controlled, and finally they can also participate in the vehicle to create technology over years. So it means that all of the users over years, the driver, the user, something like that, they can have any kind of new opportunity, new circular economy over there to get not only utilize these kind of electric vehicles as the transportation mode, but also utilize them as the energy services. So they can have any kind of another profit, which can also be another passive income for them. And also there are some services that are quite possible for both hydrogen or also electric vehicles, but I just would like to skip this one in case that you have any kind of questions, something like that. I can explain further details, something like that. This is the projects all over the world until now. This 50 projects all over the world, but I just would like to skip this one. This is also the opportunity of a vehicle grid integrations in the Indonesian case, especially for the Indonesian case. Actually, our energy systems, our electricity is basically fluctuating, it's very, very fluctuating. So we need any kind of responsive energy buffer for this one, including the hydrogens, including the vehicle, electric vehicles or vehicle to grid technology, or etc. actually. Okay, so I think I just like to end up my talk today. What we need for our country actually, decarbonization, yes, and also the energy efficiency, we need to develop that. And also the renewable energy, but we must be really wise in this case. Don't only take another country as the example. No, we need to develop our own scenario. Okay, we must be really wisdom, really wise to realize our conditions, our characteristics. Okay, we are in tropical area, which is quite humid, with this temperature is also quite high, the wind is not so blowing, or etc. So we must be really wise and also be able to finally be able to decide what kind of the best energy scenario for all of us. And also about talking about the smart systems, talking about the market transformations. So the market must be open. Market must be accessible to all of the stakeholders in case that we would like to improve the energy equity in our energy systems. And also talking about the resilience, and also finally about the policies. Thank you very much for all of your attention today. So in case that you have any questions or something that's we need to discuss further, it is my great pleasure to discuss with all of you. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, we have listened a great presentation from Mr. Muhammad Aziz. Thank you so much for Mr. Muhammad Aziz for the informative and interesting presentation. All right, ladies and gentlemen, now we come to question and answer session. We have around 10 minutes for the occasion, and we open to question first. After that, if there is still time, the audience will be given the opportunity to ask other questions. So you can submit your question on the chat box on or you can raise your hand at a Zoom meeting. And don't forget to mention your name and your affiliation. Okay, any question? Okay, maybe I wanna ask first for Mr. Muhammad Aziz. I just found out. I got an important point from the presentation. It turned out that it's not only the Internet of Things, but we also need to think about the energy. And I just found out about the term of Internet of Energy. But maybe you can explain, can sustainable energy be applied to a smaller or specific area, like in a rural area or in agriculture area?
Okay, thank you very much. Actually, yeah, it really depends on. Okay, in case that the area is quite rich of resources, including especially when we talk about the agricultural area, something like that, we can use any kind of utilize any kind of like agricultural waste or etc. And also the important thing is that how we can combine this kind of conventional technology to any kind of another technology. And when we are talking about the rural area or any kind of remote area, because usually the scale is quite small, right? The important thing is that we cannot, from very beginning, this kind of rural area or very small scale area, basically the price is quite premium. The price is quite high. So we cannot, from very beginning, we cannot assume that the price is low. No, it is the premium service that we can that we need to have. Because what? Because we cannot build any kind of large scale power generations over there. So it means that we need to develop any kind of small scale power generators, and also because the relatively because the fluctuation is quite high, it's quite huge over there. So we need any kind of energy buffers to cover that. So it means that for the rural areas, like in several countries, like in Europeans and Japan, and also I don't know like Indonesian's case, but like for the Japan's case and also for the European case, actually they usually utilize this kind of area to be any kind of the showcase for the technology. So they can utilize the renewable energy, they can utilize any kind of waste, any kind of basically like the biomass waste, whether it is from our municipal waste and any kind of agricultural waste, any kind of industrial waste, something like that, to be converted to the energy. Yeah, the price is quite high, but we would like to mention again that this kind of services is the premium services, not the common services that must be quite economic or competitive compared with the large scale area, something like that. Thank you very much. And I think like Indonesian case, because for the Indonesian case, we are laying or depending strongly on the solar, on the diesel-based power generation. So it means that we need also to communicate this kind of technology. Okay, we can utilize this kind of agricultural waste or any kind of biomass waste, but we also need to ensure that all of the system can run for 24 hours, and also it can responsibly covers the fluctuations for the demand itself. So I think utilization of renewable energy coupling with any kind of energy storage, I think that's also very important for us. Thank you very much.
Thank you very much, Mr. Muhammad Aziz. Then there is a question from Maria Al-Kiptia. What is the differences between vehicle to grid and vehicle to everything?
Okay, thank you very much. Okay, when we are talking about the vehicle to grid, usually it is abbreviated as V2G, okay? Or about the vehicle to everything, V2X. Okay, V2X can very wide definitions. V2X include V2G, include V2H, vehicle to home, vehicle to offices, V2O, or vehicle to business, V2B, or etc. So it means that basically vehicle to everything or vehicle or V2X itself is the common things. Okay, when we are talking about the V2G, so it means that the vehicle is integrated with the grid, and the vehicle itself behaves as the ancillary service to the grid. So we can provide any kind of like frequency regulations, voltage regulations, or etc. for the grid itself. That's when we are talking about the V2G. When we are talking about the small things, when the cars is only connected to the home, so usually we can call it as the V2H. So it means that the electricity communications or the electricity itself or any kind of interactions over there is only limited to the homes itself. So it doesn't go to until the grid. When we are talking about the business or the office or about the factory or actually or anything else, actually we just limit this kind of framework. So the definitions is depends on the frameworks that we are talking about.
Thank you very much. We still have 1 minute, and maybe I will asking question from Mr. Muhammad Adli Rizkullah. Does vehicle to grid or V2G will be affecting car battery life?
Yes, actually the answer is yes. Yes, okay. But according to our experiments, we did experiment for 2 years. And what we really care about there is that, yeah, there is any kind of degradations. Battery degradation, yes. But we can imagine, like the car, we use the car only for the transportations. Usually per years, we can have any degradations about 3%. Okay, when we, in case that our study that we use the cars both for the transportations and also for the vehicle to grid at the times. Finally, per years, the degradations increase by 4%. So there is any kind of increase for the degradations, but it's very small. Because what? Because when we are talking about the ancillary services provided by the electric vehicles, usually we are targeting for frequency services, frequency regulation services. Frequency regulation services, basically the price is quite high. It can be about 100 times of the normal electricity price, but the amount of the electricity is very small. It just we just need to cover this kind of fluctuations. That's the things that we did in our experiments. Thank you very much. Yes, in total, yes, there's an degradation, but the degradation is not so significant. In total, in case that we are talking about the lifetime of the cars, about 10 years, after 10 years, in case that the car is utilized for both V2G and also for transportations, finally, after 10 years, I think the capacity of the battery drops to about 75 or 80%, something like that. So actually, we can still use the cars, actually, not without further problems, I think. Thank you very much.
Okay. Maybe the time is already show 12 o'clock in Indonesia. I apologize for the limited time, so not all the questions can be asked. And then, ladies and gentlemen, finally we come to the end of our keynote session. We would like to say thank you again to our keynote presenter, Mr. Doctor of Engineering, Mr. Muhammad Aziz, for the informative and interesting talk, and to audience for active participation. And hopefully the presentation will be beneficial for everyone. Thank you for your attention. And one more time, please allow me to close with this session with wassalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, please join me to give a round of applause to Professor Aziz. Thank you for such an inspiring presentation you shared with us today. And also thank you to Mr. Fahmi for leading this sharing session. Okay, ladies and gentlemen, now you will have 1 hour break before the announcement of best papers, followed by the closing ceremony of the symposium.
Ladies and gentlemen, now we will have 1 break before the announcement of best paper, followed by the closing ceremony of the symposium. So with that, we do hope, ladies and gentlemen, will attend it, will come back again after the lunch break because we still have the announcement and the closing ceremony of the symposium. Thank you.